Problem number 10. A balloon filled with air submerged in water at a depth h experienced a buoyant force B0. The balloon is moved to a depth of 2h, where it experienced a buoyant force B. Assuming the water is incompressible and the balloon and the air are compressible, the buoyant force B satisfied next conditions. Solution for problem number 10. The buoyant force is rho v, where rho is the density of water and v is the volume of water displaced. Since the water is incompressible, rho is constant, while v decreases since the balloon and air are compressed. So it means that b must be less than b0. And this is the answer D. And this is correct solution for problem number 10. Problem number 11. A circle of a rope is spinning in outer space with an angular velocity omega 0. Transverse waves on the rope have a speed v0 as measured in the rotating reference frame where the rope is at rest. If the angular velocity of the rope is doubled, the new speed of transverse waves as measured in the rotating reference frame where the rope is at rest will be next one. Solution for problem number 11. Consider a small segment of rope. The tension force on each end of the rope provides the centripetal force, which is proportional to omega square. The wave speed is square root from tension over linear density. Linear density here is a constant and t proportional to omega square. It means that the speed proportional to omega. And this is answer C. And this is a correct solution for problem number 11. Problem number 12. A child in a circular rotating space station tosses a ball in such a way so that once the station has rotated through 1/2 rotation, the child catches the ball. From the child's point of view, which plot shows the trajectory of the ball? The child is at the bottom of the space station in the diagrams below, but only the initial location of the ball is shown. Solution for problem number 12. The child catches the ball, so the path must start and end at the child, running out choice E and A. To decide between choice B, C and D, consider the velocity the child observes at the moment that ball is thrown. At this moment, the ball is moving directly upward, while the child is moving directly to the right. So the relative velocity is directed both upward and leftward, giving choice C, and excluding B and D. Because for B we have only speed going to the center of this station, and in choice D we have only leftward motion. It is possible to solve this problem exactly, though this wasn't necessary. In polar coordinates, the radius r of the ball is linear in time, and the angle theta of the ball is also linear in time, because it is constant in the lap frame, but the child's frame rotates uniformly. Explicitly, we have r proportional to theta minus pi over 2 for theta belong from 0 to pi. And plotting this gives choice C. That was a solution for problem number 12. Problem number 13. Two blocks of masses M1 2 kilograms and M2 1 kilogram are stacked together on top of a frictionless table as shown. The coefficient of static friction between the blocks is mu s equal 0.2. What is the minimum horizontal force that must be applied to the top block to make it slide across the bottom block? Solution for problem number 13. Let's write equations for motions for the top and the bottom blocks. For top block we have mass m1 multiplied by acceleration a equal force F minus force of friction. For bottom block we have m2a equal force of friction. It means that acceleration equal force of friction divided by m2. From here we can find what is force F. Force F equal force of friction multiplied by m1 plus m2 over m2. But the maximum possible force of friction equal mu static multiplied by m1g. So when we put this to this expression, we have force F equal this expression, and when we put numbers, we have 12 newtons, which is answer D, and this is a solution for problem number 13.